Good day, good day. This is Marcin. How do you say your name?
Hello. Can you hear me,
I can
Marcin?
hear you. Can you hear me?
Yeah, I can hear you clearly.
Okay. Can you tell me how do you say your name?
It's Motakabir.
Motakabir.
Um, yeah, Motakabir. Yeah, perfect.
Good, good.
Yeah.
Okay. Yeah. Well, thank you. Thank you for spending the time. And so you were Dr. Pierce's student for how many years?
So I've been working on under Professor Pierce for like last 3 years now.
Okay. Yeah.
Yeah.
Yeah. So have you seen my TED Talk to see what we do? My side.
Yes, I also visited the website that you shared
Mm-hmm.
and like looked into, and also like I was also like you shared a link of your like the inverter project. I think like a Wikipedia type of page where like I have seen like I think you showed a model of FreeCAD of like a MOSFET on a heatsink, and you want to make the modular inverter as well. So yeah,
Yeah.
this looks very interesting. And yeah, I just wanted to know like what's your plan with this and like this and like how far you got so far and this kind of
Oh,
things and also like
yeah. We haven't
yes.
done any prototyping or anything. We haven't really built on this front. We haven't built anything. But the idea is that I mentioned we got 120 kilowatts of photovoltaics, and I was looking at just getting an off-the-shelf inverter. 120 kW inverter costs $11,000. Well, hopefully the upfront price is not bad, but the problem comes when the thing breaks, right?
Mm.
So that's the part we're trying to address. Basically, designing something for a lifetime. So if we know how we built it, we know how to fix it. That kind of thing, right? But I mean, we haven't done any prototyping. We've done, let's see, I mean, no, not even. I mean, we've done microcontroller work. We run for example, our brick press with a microcontroller, and of course, we've done 3D printing, all these kinds of things. So we're familiar with microcontrollers. In fact, we built one from scratch, just using the chip, and then made a circuit out of that to make a minimalist Arduino kind of a thing that's still programmable. So we've played around like that. What else do we do on power electronics? A little bit, like just little steam camp type of stuff. But as far as any real deal behind it, no, not haven't. So we're starting on this pretty much from scratch. But I mean, conceptually, I'm wondering why haven't really seen any good designs online. I mean, there's ones for very low power, but given that this thing can be scaled, like you just use like a 1 kilowatt MOSFET or whatever, or IGBT, and then just put a bunch of them together, say for 10 kilowatts. Well, why is that so much harder? I don't know. I think conceptually it's easy, but in practice, I don't know. So
I think like the problem comes with like the scalability is like the PCB design, like the traces and stuff. Like uh, when you are making a trace for like suppose in DC like 10 amp, 20 amp, it's fine. But when you go beyond that, like 50 amp, 100 amp, it becomes very tricky. So maybe that's why like maybe because of that, like I think maximum size of inverter, even the open source one that you can see in online, I think 2 3 kilowatt, not beyond that. And even
okay,
that one are not even grid following. Those are like off grid type of thing. Like you connect your battery and get your AC output. Like those kind of inverters, I think you can find it online, but not even the grid following one because of these technical issues that arises.
okay. So the way to solve that, in my view, is so you don't put any of that on circuit boards. You connect it all
Mhm.
through wiring and bus bars and things like that. So then you can. Okay, so you've got the brain part, which is low voltage, very minimal, fast speed stuff. So you've got the brain stage and you've got the power stage, right? So why not design it such that, for example, like you saw the model in FreeCAD. Let me share my
Yeah, I have seen that. Yeah.
yeah. Oh, by the way, do you mind if we record this for the rest of our community so that everyone can learn?
Yeah, sure, sure.
Mm-hmm. Right. So I'm just going to share my screen just for the public and for you as well here. Let's see. Um, Let me just do that. Where is my present entire screen? Okay. So for example, if you look at um, yeah, that that's this is our beautiful thing. So okay, so you've got little elements like this. So that's power, and imagine you can make this whatever size and package of power element, whatever size heat sink that you require, whether air cooled or water cooled, and you're talking then about some mechanism to socket this thing, or put the three leads into a socket or something so it's quick connectable, and then you've got fat cables, or maybe this goes to a bus bar, and then you've got fat cables going to the rest. So you're not putting any of this power handling stuff on circuit boards.
Unnecessary. Yeah.
Definitely because you've got, uh, I think what you're referring to, let's see, stop sharing. What you're referring to is the difficulty of making circuit boards that handle a lot of current.
Yeah.
Now, would that be possible to you got your brain and then you've got your power handling elements which are designed like for max 3D printing. So let's print all these 3D printed holders and even terminals. Like we actually did print some kind of a power electronics construction set, like a basic board where you can screw in and make a lot of connections on it. So we do have a little bit of experience. That's I mean that's easy. Just 3D printing and even with screws and or more professional terminals. But as with as simple as say a quarter-inch stainless steel bolt as a clamp down, you can connect two wires in a 3D printed structure, right? And there you got 100 amps or something or whatever. So so things like that. How does that sound to you? What do you think?
One thing that you were 100% correct is like you have to like even if you go with PCB,
Mm-hmm.
you have to keep your control circuit and your power circuit separated. So they are meant to be separated, and you have to ensure that. So this can be a better option to do that. And also like I think like if you go like maybe for transistor, this is the only solution that you can come with. But if you are referring to like IGBT maybe they sometimes come with these kind of blocks, built-in blocks, like a IGBT already with a like maybe for that, I think they already come with a heat sink and
Mm-hmm.
maybe uh, to like bridge connection of IGBT in a single block. So maybe it will be further easier. Maybe you don't need to build it from the scratch like heatsink and the MOSFET. For the MOSFET level, I think it's fine until like 1, 2, 3 kilowatt. But beyond that, I think you need to move toward like IGBT because of like the advantage that it comes with. And I think there are several in market. They come in like bridge setup already, like multiple of IGBTs forming a bridge, half bridge or full bridge, and they comes like these kind of blocks. I think I'm sure like I have seen those. So I think the idea that you already have, I think that can be like scalable in terms of IGBT as well. And yeah, that actually I think it is very very possible. But another thing that you might need to consider is like the driver circuit that you will have.
Mm-hmm, mm-hmm.
So it might be different for suppose one or two MOSFET in parallel, and when you want to scale it for like 10 MOSFET, maybe one driver circuit won't be sufficient. Maybe you need to modify that circuit. So I think there would be some limitations, but I think it is very possible to like maybe for if you design a 1 kilowatt inverter, maybe that can be scalable up to 5. Then for 6 to 10 you might need a different up at least the control circuit. Then for 10 to 20 you might need a different type. So I'm just saying these kind of rough numbers, but maybe this is one that comes to my mind. But it is like I'm sure like you are on the right path, and I think it is possible to make it like this modular form. And yeah, in terms of IGBT even.
Okay. Um, can you do an IGBT that's doable from 1 to 10 units, and a single same driver could drive all those, so you can oversize the driver for 1 to 10? Can you do that?
So that's like I think it's doable. Like maybe you oversize it for like smaller inverter, but it is adequate for like larger inverter. Yes, I think that's possible. But like I don't have enough experience with IGBT. I just know the theory there, but never built a circuit with that. So yeah, I think I can look into it and like maybe send you more information later. I just don't want to like comment on that right now because like I don't have like hardware experience of working with IGBT.
When you did the DC-DC converter for for the project, what did you use? Did you use MOSFETs?
Yeah, MOSFETs. Even the inverter that we built, it was MOSFET. And there was another project where we was planning to scale up the DC to DC converter to like 5 kilowatt scale. So we encountered some issue, like of course the PCB related issue. So then what we did was like we had a 5 kilowatt AC to DC converter in our facility that was like three phase. So we developed like we ordered three Victron inverter, then uh, formed a three phase network of like 7 kilowatt, and then used the existing AC to DC converter to show the demo, like complete the demo for like the hydrogen production. So we did that temporarily, but our plan behind was like let's build a small DC to DC converter and then scale it up to like 5 kilowatt. So yeah, I think at that point I didn't had like enough confidence on my design. Like okay, I can start building a 5 kilowatt DC to DC converter. And I'm not sure like whether you have faced the same issue in US or not, but in Canada they are very very scared of like anything you do. If it doesn't have like CSA approval, it is so difficult to get permission to do even experiments. It's like that's why like we had to go to that path. Like we ordered everything CSA approved, then like we don't have even any permission to connect any of our device if that exceeds 48 volt DC, or in terms of AC, if that exceeds 500 watt, we are not allowed to do any kind of testing connected to utility in our lab.
Yeah, and of course we can get by that because we can experiment on off-grid applications first, right? So we don't
Yeah.
have to worry about. That's another story. That we can do as a subsequent phase, but not yet. Um, as far as doing single phase versus like split phase 120 240, would you be able to do that, or any voltage that we need? Like say Say we wanted to go to three phase, 600 volts. What is it? It's like 640 volts, three phase. Um, is the design get much more complicated if you start going into multiple phases?
No, like I would say like it's just I think for three phase you need three bridge network and one like microcontroller should be fine. Like if you are considering like STM32 microcontrollers, those should be adequate enough to make a three phase network. And it's not like even I think there are like some motor controllers that are three phase, like very small scale, even 10, 100 watt, 200 watt, and it's very easy to make. But the problem, I don't think there is any problem to make a three phase network. It's just the problem arises if you want to make a grid following one, or now the latest trend is like grid forming one. So in that case, you need a phase lock loop where it always tracks the phase of your utility or uh, the main, and then creating that AC signal in like three phase or single phase, whatever you were saying, to synchronize with the grid. So there the complexity arises. But if you were making an off-grid inverter, I think you can even make it on your breadboard using Arduino even. Just Arduino, four MOSFET or two six MOSFET, you can make your three phase from a battery. You can make your three phase supply. Then you, if you want to reduce the harmonics or the ripple, make it more sinusoidal, maybe more complex circuitry like a LC filter, LCL filter comes in. But apart from that, making a off-grid inverter is very easy. When it comes to the grid connected, then that controller becomes a little bit tricky because you need to synchronize with the grid. So that's the tricky part. And also like there are several issues that also comes, like sometimes like how much you are allowed to supply to the grid, and how if you are allowed to even absorb any reactive power or not. So those kind of control things that comes in, like you have to like I think I don't want to like make it more complex, but there are like if you are going into three phase, then controlling current or voltage of each phase is not possible. So you have to do the Park and Clark transformation. Then from a three phase um, signal, you convert that into a DC signal of two quantity, and one is direct, one is D axis, one is Q axis, and these two axes of voltage or current you can control, and like a normal DC controller, like a PID controller you can use, and then you can control the active power and reactive power, how much power you want to push from your inverter to the grid. So it's a little bit tricky if you are trying to make a three phase uh, uh, inverter, but grid connected. But if you are making a three phase or single phase grid off grid inverter, that's very much easy. But the complexity is not in the uh, the power circuit. It's always the control circuit that the complexity comes from. The power circuit always remains the same. If it's a grid following one, grid forming one, or a off grid one, the power circuit of like MOSFETs and IGBT, they always remains the same.
Okay. Can an Arduino 8-bit do a basic off-grid inverter to any power?
Sorry.
Could an Arduino inverter, like Arduino Mega,
Mhm.
do an off-grid inverter that's capable of doing any power like 100 kilowatts? Pending you, of course, having the right power elements. Or is that we're talking into limits of processing speed? No, I mean you're still talking about no.
No, I would say the processing power. I think it's good enough. It's just gonna be limited by the MOSFET drivers. I don't think there is anything like suppose you are making a single phase inverter.
Yeah.
I think like uh, you need to fed two pairs of MOSFETs mostly. So in that case, you need literally like two digital or like PWM pins that gonna supply the like create the pulse that gonna be uh,
For the driver.
controlling, yeah, controlling the supplying to the driver. So the driver would be responsible for most of the heavy lifting here. And of course you want to control the output current, and of course you want to monitor the output voltage and like adjust it, so there would be some feedback loops. But I think uh, the way like even I don't see any complexity comes into the MOSFET, sorry, not into the Arduino Nano or Arduino Uno or Arduino Mega. I think they each of them can pull this off, like designing the inverter. But the problem will be like the complexity will arise from the MOSFET driver itself, which is independent of the processing power that you need. It's like dependent on Arduino Nano, but it is like the how much it can uh, like how many MOSFET it can drive and what are the other complexity arises, that depends on the MOSFET driver, I guess. So yeah, I
So
think
the answer
just
is we should be able to use an Arduino controller to do that.
yes, of course. But I would suggest to like look for STM32 because the process, the like because like they are same type of like due to the like in current scenario, like I started my like microcontroller thing with Arduino, then I moved to ESP, but like lastly I was using with STM32. The I think this kind of power electronics like any kind of device if you are developing, I think STM32 would be better because like they have better ADC. So if you are like want to monitor the output voltage or output current, you will get more precise. Like some of the ADC are like 24-bit, so you have a built-in ADC that is reliable in STM32. But in Arduino, you might need to use an external one. So I would suggest that starting with STM would be a better option for any kind of power electronics. I think it is also respected in yeah, power electronics industry as well. They in some devices, the companies prefer to use STM over.
Can you look at the link? So you're talking about something like that, which only costs $1 for the microprocessor?
I'm looking into it. Oh wait,
Aha, so you want better measurement feedback capacity.
it's like more precision
Yeah.
and more reliable for power electronics application.
Okay.
And like uh, there are some STM32 that can be programmed by Arduino IDE for the start, and later you might need to switch to STM Cube.
What's the programming environment for SDM called?
I think it's STM Cube MX.
Let's see if I Google SDM programming environment.
MX, I guess, but yeah, STM32 Cube
Uh-huh.
MX.
CubeMX. Uh-huh. Oh, it's even graphical.
Yeah,
Oh, great. Oh, wow. So you... Uh-huh. Okay, cool. And the chip itself costs how much?
it's like the so if you are thinking about using an evaluation board, then it depends. But if you are thinking about talking about the chip itself, the microcontroller unit, I think that's like almost comparable price with ESP32 or Arduino. They are like almost similar.
in the link that I showed you when it said that the under a dollar figures, was that actually the figure, the cost for the just the microcontroller chip? Price from, it says at the top. Oh, for
So the
32
microcontroller.
units. Ah, okay. So, but on the
Yeah,
market,
mm. But you can find some evaluation board as well, like Arduino Mega. They have a Arduino chip, like 80 mega chip on the Arduino Mega. So STM32 has their evaluation board. They are for developers. So you work with that, test your circuit, then you build the circuit using the microcontroller and the peripherals. You make your PCB with that. So the cost of the evaluation board may be ranging from 30 to 70. I'm talking about Canadian, so USD might be cheaper, but it's not that different from Arduino Arduino lineup, but it's not that available as well. So maybe in DGK they have like limit like maximum 10 you can order at the same time. It's and you will see like it's mentioned like it's not for mass production or any other application. It's only for developers. So for like testing purpose, it's fine. And then you build your own circuit and like in any of the in any suppose in Arduino Mega or Arduino Uno, Arduino Nano, you have a onboard, uh, sorry, onboard USB to connect, and then see you are to serial converter. Then this kind of like onboard these things that you might not need to run an inverter just for programming purpose you might need. So you can just in when you develop your final inverter, you don't need to put a uh, programmer on board. You can just
yeah.
program it and then place the microcontroller on the board. So in
Okay.
that case, your cost will be reduced significantly.
Okay. I mean, what is a like for example when it said like a 65 cents for one of those and 10,000 quantity unit? What is it on the like units of 10 and things? What's the cost? Is it like a couple of dollars or something?
Yes, yes, yes. I think you can see that in DigiKey. So
Okay, the G key. Let's say what do we got on DigiKey for example? Uh,
yeah, these are like one to it starts from one and then $2 3. So
okay.
I think they're almost in same range as Arduino.
Yeah. Yeah. Is there any board that has like the
STM.
equivalent Arduino to an Arduino which has all the different onboard infrastructure? Is there one that is there a microprocessor microcontroller with STM32?
Yes, yes. So if you search in DigiKey, you will see evaluation board or kits. So if you search in STM, there will be top results. And instead of going into microcontroller, you select evaluation board or kits. So they call it Nucleo board. So they have their proprietary uh, microcontroller board as well. So they are called like Nucleo board. I can share one or two with you.
Okay, yeah, I see one for like 66 bucks.
Mhm.
STM32 evaluation board. Now tell me again. For all the measurements that we want to do for simple, just without getting into on grid, if we're off grid, is the Arduino version, is that give you a disadvantage? Like, I mean, how much do you lose in terms of the feedback, critical feedback loops?
I think it's Arduino should be fine as well. It's just the precise control may be absent, and like it comes when like if you want a like reliable value on the screen, like how much power it's consuming, how much current it is, or if you want to see like a oscilloscope, like what's the output signal looks like, which is not necessary mostly. So for those kind of applications, like if you want not looking for any precise control over current and voltage, you just want to supply power what is needed by the load. I think Arduino can pull this off, and I think I can share on one of our like there is a so you can even start from not even from the Arduino. There is one board that I forgot the name. Just 1 minute. I think it's EG 2004.
Because one of the other ideas is that because we already use Arduinos in other applications, it's about product ecology, meaning that if we have those already, that's not an extra part in our overall set. So that's how we look at it. We say, okay, let's minimize for the global village construction set, minimize the total number of parts so that somebody can replicate and have robust backup. Like say one thing fails, you can actually take the component from another system to retrofit. Does that make sense?
Yep. I think for if you are doing off grid, I think Arduino can pull this off. But if you are trying to do grid connected, then I would recommend like maybe start using STM32, because the circuit or maybe the mostly the control circuit would get complex and complex for like once you move from single phase to three phase and grid connection and stuff. Then it's better to use STM32. But for maybe off grid, I think Arduino Mega or Arduino Uno can pull this off easily.
Mm-hmm. Mm-hmm.
And I think problem with Arduino Nano is like Arduino Nano processing power is enough, but the PWM bits that you can I think that is a little bit less because of like 12 bit sorry 12 bit digital pins being 12 bit digital pins, so it doesn't allow you to precisely generate PWM signal, but I think Arduino Uno or Mega should be sufficient enough.
Mm-hmm. Mm-hmm.
But for grid connected, I guess, or grid following, I guess it's better to use or start with STM32, because like I was working on that, designing a micro inverter. So there is already a open source one available in it is like, so what one guy I think from Europe was trying to replicate one of the commercial microinverter. I don't think he finished it. He did several versions in GitHub, and like he tried to make a microinverter, but he tried several things. But at the end, I don't think he achieved what he was expecting at the beginning. But he was using STM32, and he I think the whole design is there, but I think he couldn't finish the whole experiment.
Yeah.
But all the design files, all the PCBs are there. But for the initial, so I was looking into that and started to design the microinverter using STM32. So I just was able to do one thing before I joined here in Hamilton. So before that, I was able to make a power monitoring system. So what my plan was, like for grid following, not off grid. For grid following, you need to monitor the grid. So where you gonna inject your active and reactive power. So for monitoring, I was trying to develop a power monitoring device. So which so there are several in Amazon, like $20-$30. You can like find a AC power monitoring device which will give you like what is the voltage, what is the current, what is the power factor, what is the frequency, this kind of stuff. So I tried to make that with the oscilloscope on it. That means you can see the waveform of your current, of your voltage, and that was my primary goal, to build that, and then based on that to design the inverter to feed or synchronize my output voltage and current of my inverter to the grid. So that was my plan. So I was initially using STM32 for that, but I couldn't finish that. But I think for anything grid connected, I would suggest to go with STM. Otherwise, for grid off-grid application, I think Arduino should be sufficient.
Mm-hmm. And then, what about using then higher power processors like from BeagleBone? Because those chips can be had, right? We can get BeagleBone microprocessors, but those are like gigahertz or so, right? And but they're open source. They say they're not open source on the at the level of the actual chip design. Well, only like the BeagleBone board is so-called open source, but none of this stuff is open in a true way, right? Is there any advantage to going to something like a BeagleBone thing at this point? Not really.
So the thing is, like, if I had completed the project, then I could have said you like what are the limitations
Yeah.
in STM32. Like I can say you like what are the limitations in Arduino. Like of course it's gonna be less precise, less reliable, but I'm not sure what are the limitations of STM32 and what would be the benefit to go into
Yeah.
uh, Gigabyte. And another thing, one limitations that STM32 might have that you might think is like it doesn't allow you like Wi-Fi connectivity, Bluetooth connectivity that are like very common or one of the requirement nowadays. Like if you want to monitor your device, like inverters, you should need to connect to Wi-Fi or connect to a server or at least Bluetooth. So those are lacking in STM32. But you can just put a ESP board on your inverter and just communicate with STM32, and then the ESP32 can communicate with the server. This is like pretty common. So I think you can tackle that, but I'm not sure like what would be the extra benefit that you can make out of the Gigabone, because like you need precise control, of course, but still the output signal, like the output waveform is 60 hertz. It's not megahertz range. Like you don't need that range of uh, powerful processor, but still it should be reliable enough that whatever you measure, like in Arduino, what we do usually to tackle the precision issue, we take three values or five values and then average it out, because one or two values might be a little bit off. So in terms of inverted design, if you use STM, you don't need to do that. You just take one raw data and you can make the controller out of it. Like, okay, that's the final. We don't need multiple values, then average it out. So that's the reliability. But I don't think going to like gigahertz level of processing is required for like any power electronics application. At least in terms of like inverter. But I'm
So
not. I can.
so you say that some pickup loops or whatever, however you're measuring current or voltage. I mean, what's the bit depth of Arduino Mega?
What is the?
16.
Sorry.
Arduino Mega is 16-bit. So, um, I mean, 16 bits. I mean, that's pretty accurate. Why do you need to average that? I mean, what's the resolution of 16 bits? That's pretty.
That's pretty good. But I have seen like, so if you just make so what I encountered was like even with ESP32, they are also 16-bit and like way powerful than Arduino. But what I did was like that power monitoring thing that I was telling you. Like I was measuring raw data, raw voltage and current, sampling it, and just showing it on a display, LCD display, or in your serial, in any kind of plotter. You will see like the sinusoidal wave is not as what the grid sine wave would look like, because you will see some deviation. If it's
But
a
isn't
pure,
hold on a second? Isn't that a function? Oh wait, that's not a function of the driver. That's actually a function of the signal that the Arduino is putting out.
no, I'm not talking about the output. I'm talking about
Oh,
the feedback that you're gonna get
feedback.
from like feedback. So that's in that way, I think STM would be more reliable. But I think Arduino Mega would be like, that's why, like if you are making an off grid, I think Arduino Mega should be sufficient enough as well. I think it's more precise than at least Arduino Uno and Nano.
Okay. Is the Arduino Mega actually generating the sinusoidal shape, or is it a function of the
No,
driver?
no, it's not the function of the driver. It's the function of the Arduino Nano or Arduino Mega would be to generate the pulses.
Yeah.
So the pulses would be like a square pulse with different wave pulse width.
Yeah.
And so how the Mega would work is like you will select the uh, you will select the frequency at which the PWM pulse will be generated. Usually it's like in 50 kilohertz is like minimum, or 30 kilohertz is minimum, because like you don't want to switch your MOSFET very like in lower frequency or even very high frequency. Both of them has limitations. So it's the sweet spot is between 30 kilohertz to 100 kilohertz. So within that, you need to generate your PWM pulse. So the MOSFET will do that. And then according to that, then the MOSFET driver will operate the um, MOSFET. So it will turn on and off each pair of MOSFET at different intervals. At one time, one pair of MOSFET will be on, and in next, like in every, so whatever the frequency of your output AC is required, suppose it's 60 hertz, that means 16 millisecond. So for 16 millisecond, one pair of MOSFET will be on, and for next 16 millisecond, another pair of MOSFET will be on. So this how you make your wave shape like sinusoidal.
Do
Uh,
you get Arduino Mega doesn't have any issues with making a perfect sinusoidal wave, or is there defects in it?
So
Pure sine wave.
even if you use a Arduino Nano, it won't be able to make this pure sinusoidal. It will make so if you can think of like a MOSFET, it will be on and off. So there is no way you can control, like it will be like staircase type of signal.
Yeah.
So it's not going to be sinusoidal. Then you have to feed that into a LCL filter, like like I think it's first an inductor, then a capacitor, then an inductor. So and then it will convert that staircase signal into a sinusoidal, pure sinusoidal. So if you want to have a pure sinusoidal output, I think your inverter will be bulky because of those filtration. But if you buy a cheap uh, inverter from Amazon, like 30, 50 dollar, you can see their output. They are not pure sinusoidal, they are staircase. So if you want to have pure sinusoidal, then you have to put those components like inductor and capacitors, and they get bulky as your power rating goes up.
How much, if you don't have the pure sine wave, what power loss is associated without having that? Is there actually a power loss if you don't have a pure sine wave?
It depends on the device that you are operating. If it's an electronics device, I don't think they have any kind of issue uh, running on like non-pure sinusoid, like non-sinusoidal waveform. But there are some devices that uh, might be generate more heat if you apply non-sinusoidal waveform. Suppose like a motor, maybe they won't perform well if it were like a pure sinusoidal. Maybe there will be more heat. So it's not the loss within the inverter. It's better to not having those filters because they are uh, not doing anything extra in terms of like generating sinusoid, generating AC signal, but it's for the betterment of like what type of load you want to connect, and
And
and if you
also,
want to,
resistive loads absolutely doesn't matter, right?
most of the cases no, most of the cases no, especially if you are driving like if you are using a electronic load, mostly they are susceptible to these kind of things because like either way they're gonna convert it back to DC. So they're not gonna use it in AC form. So it doesn't matter that much. But if it's a inductive device or
How about
AMI,
so two use cases: induction furnace. I want to run a 50 kilowatt induction furnace. Do those convert to DC first?
no, I don't think so. No, I don't think so. But I can have a look in it. And also, like if you are thinking about grid farming, then there is a strict restriction about like how much harmonics your output AC can have. It's like I think there is a IEEE 519 standard. I think that allows you maximum 5% of THD. So you need to maintain that, otherwise it won't meet the criteria. So if you are thinking about grid connected inverter design, then it becomes very
Yeah,
uh,
yeah, that makes
essential.
sense. Mm-hmm, mm-hmm. What's Can you put? You said you don't have so much experience with the IGBTs for the MOSFETs. What's the highest power that we can you'd recommend doing the units of a scalable inverter with MOSFETs? Do they make like are they like 5 kilowatt units, like 10 kilowatt unit MOSFETs? No, is that too large?
So how you do it is like you. So I mentioned you like for a basic single phase inverter you need four MOSFETs, right? So there would be like two of them will be in uh, so two of them will operate at the same time. So you need four MOSFETs, and each of the MOSFETs current rating is limited. So suppose like if you using like 100 amp MOSFET, so if you want to increase the current limit instead of going for a bigger MOSFET or costly expensive MOSFET, you just put two of them in parallel. So they share the current. So I think that's the go-to move. Like if you develop a 1 kilowatt inverter, you just go with like one MOSFET in each leg. But if you are thinking of developing a 2 kilowatt, then maybe put two MOSFET on each leg. So instead of just increasing, like going for a MOSFET that can handle more current, you just put similar MOSFET of same type, two of them in each leg that can like increase your inverter size easily. So that option that you have, I think that you should look first rather than going for a like inverter with sorry MOSFET with higher current rating. First, you select the highest MOSFET that you want to work with, and then maybe for jumping from 2 kilowatt to 4 kilowatt, instead of one MOSFET, you just put two MOSFET in parallel. I think in your modular form, I think that makes more sense. Otherwise, if you want to use different MOSFET, the heat dissipation, heat sink or the temperature control measure might be different, and it becomes more sensitive to that. So if you want to stick to one type of heat sink or cooling methodology, then maybe using multiple of those MOSFETs in parallel is better solution than jumping into a different MOSFET entirely,
Mm-hmm.
because they need different treatment, as well as the driver circuit may be changed as well.
Mm-hmm. Typical voltages when we if we design an inverter for a long string of photovoltaics, what are the practical voltage limits? We're talking about 600, or would it be more like 1,000? Or are we looking at like 600 because of the current, because of the voltage capacity of wires?
So you are talking about the DC voltage, right?
Yep.
So there is a minimum requirement for. So it depends on if you. So you want a off-grid inverter, but without any battery, if I'm not wrong.
Yeah, it could be capable of going without batteries. Yeah.
So if you are going without battery, then of course having a higher voltage at DC side, that makes more sense. And for single phase, if you are aiming for like 120 volt, then maybe 200 volt should be good enough, and higher than that, it's fine as well. But there is a limitations like it's like root over three. If you like 1.7 something that you need to have at your DC side available to generate a AC signal because of the RMS. So that's why like maybe for 120 volt it's around 180 DC it's required. If you are going for 230, maybe 400 is required, but you can go above and then step it down during the inversion process as well, that you can do, but minimum of that DC voltage would be necessary. And if you are considering battery, then I think 48 volt is maximum that you should aim for. Like the PV connected to battery, the battery then connected to the inverter generates AC of 120 volt
Yeah.
or 240 volt.
That wouldn't be scalable for like 100 kilowatts, so that's hard to. I mean,
No, no,
no, no, no. You want
that's
to
not.
start with the ability to handle large amounts of power for for a village. Um, so
Then I think so. How the PV would work is like you need at least one storage or like backup, because PV is like the nature of PV is not stable at all, even less than wind. So I would suggest like either you need to consider using battery
yeah,
or
grid.
grid. So if you are initially building an inverter with battery, then you can go off grid. And if you are planning to skip the battery, then you have to consider the grid. Otherwise, reliable power is like very tricky. Like making an off-grid inverter only on PV and to handle that large amount of power, I think the fluctuation will be massive.
Yeah, the fluctuation, of course, would be massive, um, but that could be addressed by on-demand loads. Like if there's no power, the load goes off, and design a system around that. So there's ways to go around. Like for example, we do we melt steel when there's sun. If it goes off, it goes off. I mean, we don't have to get into the details of that, but
Yeah, but the problem with PV is like, so you need to consider some amount of storage or backup,
yeah, yeah,
because like it's not like suppose the PV in the morning it will be 6 kilowatt, in evening it will be 4 kilowatt, and during night it will be zero. It's not like that. It's like that in average, but if you see the minute wise plot or even the second wise plot at like suppose 11 a.m. in the morning, it's uh, generating 5 kilowatt. 11:01, it might generate 2 kilowatt.
yeah, yeah.
So it's that much of fluctuating. Like to tackle that without having any backup, it's impossible because of like the uh, shading, maybe for the due to the cloud, due to the pattern of sunlight, anything. So the fluctuation is massive. Like
Yeah,
every
yeah.
second, I think second is a very big expectation. Every 20 second or sorry, every second or every minute maybe it changes, and it changes drastically. So if you average it out, you might make some plan out of it, but in reality without any backup you cannot make any
Yeah,
plan with CPA.
right. What what's a general figure for if you want to, like, what do they recommend for battery backup? If we run in, say, 100 kilowatts of solar, what's the backup system that I should have to regulate power throughout the day? What would you suggest would be like 10 kilowatts? Would that be enough, or 20 kilowatts? Kilowatt kilowatt hours backup. Would 20 kilowatt hour be enough? One fifth the actual power. So if the
It
dust
would.
goes over, you can back up 20%, 100% for an hour.
Uh,
You can back up 20% for an hour.
Yeah, like I think for I think they call it, there is a term, I forgot the term, like smoothing factor or something.
Yeah, yeah.
Like it's not backup. It's
Yeah,
like
smoothing factor.
yeah, so it depends. So for that, if you're using a battery only for smoothing purpose, I don't think you need a large amount of battery. But if you want to get a stable power, like stable backup, then the size of the battery,
Yeah.
it's
I think at that point, I think we go smoothing with batteries and then backup with a generator.
that
Um,
can be.
and for the smoothing power, like, would you say like 20% is enough or not really?
So it's, you can go with your instinct, or I think you won't find a like a genuine thumb of rule that will mention you like what would be the size. But I can go through like one or two papers, from IEEE maybe, like if they already have some standard, if in terms of like smoothing. I think only the where it is applicable is like power plants. They don't. I think they might use a smoothing factor, and I think I can, if they have like a thumb of rule or some standard that they follow, I can share with you. But I haven't.
Yeah, yeah. Yeah,
Haven't.
and
I
this would
haven't.
be a thing which we test over time how well it works in terms of what kind of backup size we need. And then, of course, if you have a generator, are generators capable of like instant turn on? Like, is that easy, or that's a trick where you basically have to have it running the whole time?
The generators nowadays, like if you just put a transfer switch, like you don't have enough energy back producing, the transfer switch will switch from the inverter or the PV to the generator, and it will turn on the generator as well. So I think it's not like time consuming, or you don't need to be there, or like there are enough controller available on market, like they can sense, first of all they can sense whether you have adequate backup as in your PV or not, what's your demand is, and based on that it can switch between solar and generator,
Right.
or solar generator and utility. So I think there are several controllers or transfer switch they call it,
Yeah.
that are already there, and it is programmable. Like it can auto start and auto shut down.
Yeah.
Most of these transmitters are.
Yeah. Hmm. Yeah. Um, as far as the microinverters, they are you designing them to be put on every single photovoltaic panel, or you get a few
Yes, yes, that was the plan. Was like uh, the plan was one of like you connect multiple of the PV panel. You can like each of them will have one inverter, and the way we have MC4 connectors, there
Mm-hmm.
will be connectors, but that will be connecting two modules in terms of like to share AC uh, current. So both of them inverter. So suppose you connect one of the inverter to the grid, so that will follow the grid's voltage or current wave shape. So it will synchronize with the grid. Then you plug in your next inverter to the first one. So it will synchronize according to the first inverter. So the synchronism is required. Either it's between the modules or with the grid. So they will synchronize with themselves, and you can literally connect multiple of these inverters in series or in parallel. They can share that, and the benefit that it comes with is like the cable size. Being in AC and higher voltage level, it allows you to connect. And another benefit that it comes with, like having an inverter on the module, you can literally suppose, like, one of the idea of Professor Pierce was like fence PV. So you put PV on the fence, and then if you think about like rest of your PV is on your roof, how you connect that? So that means big DC cable you are running from your fence area to the your main room where the inverter is there, and on your roof you have the rest of the panels. But if you have AC, like microinverter, so you might have an outlet on your near your fence for maybe a water hose. Sorry, for watering purpose, you have a power outlet there. You just made the connection there because like it's generating AC and it gonna supply. So where you supposed to deliver power, instead that the same line will be used to carry the power back to your main house, because there is no rule like which direction current gonna flow. It depends on like where the generator is. If it's connected to your on your fence and you connect your in microinverter into that outlet, it will send power back to the house and supply to the rest of your load of your house. So that was the idea or the benefit of microinverter comes in. If you are thinking of putting them on your roof, I would say like no. I think it's still DC or full inverter, full grid connected inverter will be economical. But if you are thinking about those kind of like you just want to put two panels or three panels in a remote area, then maybe there is a already existing facility of like AC outlet there. You just plug in your microinverter. You don't need to rely on anything. But if you are making a centralized inverter system, then maybe a big inverter instead of those microinverters makes more sense.
Well, yeah, because I mean, for microinverters, just the number of them that you need is, unless the cost can go way down, can it?
It can, but compared to the cost of like
Right.
the modules are limited. Like each of the module is like 400 watt, so
Yeah.
you cannot like, so you have to use like if you are using 40 modules for 10 kilowatt, that means you need 40 times the number of inverters. So even if you lower the price, and that means 40 microcontroller on each. So yeah, you can get away with a smaller MOSFET, but number of circuitry or component required would be the same. So you can go away with smaller or cheap components, but still using like having same circuit in 40 different modules will cost you more
Yeah.
than a
Do you see any
single.
issue, like in terms of the balancing factor? If we're running applications like an induction furnace or a lime kiln, can they go with the sun? Clouds go over, it goes to 20% power. Okay, it sounds fine to me. Is that okay? Or do you see problems with that? It just means that
So
it's going to take longer to heat up or longer to complete the process.
it depends. Like if you made the induction heater by yourself, that is like the thing. Like if you are talking about some commercial one, then
Yeah, it'll be
I'm not sure.
right.
I'm not sure. But if you have the control over your the device that you made,
Yeah,
if you have one, then I think I don't see any problem in that. Like you delay the heating time, it's fine.
right. Fortunately, we need an open source infrastructure for all of this, so this becomes a larger project. Yeah, but that's where we need to arrive at anyway. Yeah, but in the meantime, let's go with. I mean, to do a simple inverter that's off grid. I mean, no big deal. I think that's a pretty simple proposition. Would you go with MOSFETs or IGBTs right away? Like, what's with the MOSFETs?
So I
What's the
built one using a MOSFET. I can share the
yeah?
paper with you. It was 500 watt, and there is a online. Uh, Sorry,
So does that mean I can do 1 kilowatt with two in parallel with the same driver?
no, even the same driver is good for like 5 kilowatt. So
There you
just
go.
let me share. So
So
let
up to
me
10 of them.
share.
Awesome.
This is the article that I made. But it was one limitations of that was like the transformer size. There is a transformer because it was battery backup. So the battery was like 24 volt, but it could have been made like 48 volt. And the transformer steps up the voltage to like 120 volt. So the transformer size becoming bulky. So that was one of the limitations, but that could have like I shared the paper with you. So if you see that paper, our purpose was to make a inverter or a plasma generator, plasma reactor. Sorry. So what we did, there is a Chinese PCB module that is called EGS002. So it has the uh, MOSFET driver and the microcontroller you need. And you just make the circuit PCB depending on how much what's your inverter size would be. So if you so you can see like there are 8 MOSFETs because I wanted to make a 1 kilowatt inverter. If you want to go up, you choose a larger MOSFET and multiple. Maybe instead of two, you put 3 MOSFET there, and that's it. It can like the same module can drive up to like 5 kilowatt. It's not open source, but it's not programmable, I would say. But you can make this that easy AS002 board using Arduino Mega because the microcontroller that they are using in their chip is less powerful than a Arduino chip.
Inverter schematic, PCB design in KiCad, which we like. MOSFET. Wait, that's a inverter, DC to DC inverter. You're saying? No,
Oh,
220 volt inverter operating on 24 volts DC.
DC to AC.
Where does the DC to AC come in? Where you said this paper was about a DC to DC converter?
Oh, this is not the DC to DC converter one. There is another one that was for. So I can share you that one as well.
Oh wait,
I can,
so you're saying in here we already have a design for what we need as a particular example.
but this one doesn't have Arduino Nano or
Mm-hmm.
Arduino Mega. So this one has a board. If you see EGS002, so that's good enough for 5 kilowatt, but that's not open source.
Mm-hmm.
You can the open source is rest of the design. Like they give you the spec sheet, you can make your circuit as you want, but you cannot program the microcontroller because it's already on a proprietary board which has the microcontroller and the MOSFET driver,
Mm-hmm.
and it is isolated from the power circuit. I designed the power circuit, combined them, and then made the PCB, made the rest of the testing. There were several other issues, but this is one of the example that you can
Oh.
consider. But you can the next step would be like if I had to design the same thing, maybe instead of going with that Chinese MOSFET driver or inverter driver, I will make the driver by myself.
Yeah.
So then it becomes totally open source.
Yeah.
So this is one of the example, and we have several paper in like International Journal of Hydrogen. I'll share those two as well. One of them was DC to DC converter, and one was like 5 kilowatt inverter that I was talking to you about that we couldn't make, but we went with a proprietary solution.
Why couldn't you make it?
I told you like I wasn't confident enough to like it was like 3 months before my defense, so I wasn't confident enough like a 5 kilowatt inverter. And one of the problem was like Western won't allow us
Yeah.
to test it, and it was funded by IESO, so one of the utility company here in Canada. So they won't even like that idea, like going totally open source. So that's why we
Sorry,
finally
they weren't particularly fond of open source. You said. Sorry.
they are everyone likes it, but they don't trust. That's the problem at the
Okay.
beginning. So yeah, I think the trust is one of the issue,
Yeah.
at least in high power. So I think people can risk even medical device with open source, But 5 kilowatt inverter, 10 kilowatt inverter, I think people surely gonna freak out. Or
Um,
100 kilowatt, of course.
there
But
are
they can easily consume cheap Chinese product. They will trust that because it. But maybe if you are making open source, maybe at the beginning you might it might be a hurdle to get approval if you want to
this
go
is for
into
an
as
inverter.
fast. Now for upgrade even it's fine,
Okay, this
I
is
guess.
okay.
But for grid connected, getting the approvals are tricky. Here
Um,
in Canada at least. Let me share you those papers as well.
wow, so
Sorry
you've been
about
working
this.
off this one already. Um, now, sorry, which is the driver there? Let's see, what's the driver?
The
The
driver was already on the board, so you cannot see that. So the board is proprietary. That
mm-hmm,
was the problem.
mm-hmm, okay. Tell me about the just quickly about the transformers. Uh, where do I see the transformer in this one? I do not.
So it's shared to where in the paper?
Yeah, in the paper you showed me for the 230 volt inverter on 24
So
volt.
it's in figure 16.
Are you saying so? This is the paper that you wrote this paper, but you actually never produced the inverter, or this was made, this was built.
So which one?
Oh, the one
Uh,
sciencedirect.com, um, the open source portable solar power supply for plasma generators.
no, we made this.
Okay.
This one was inverter, but if you see another paper, which was DC to DC converter.
Yeah.
So we made that in a small scale. That was one of the paper in Hydrogen Journal, and in the next another one was named experimental integration of FPV system electrolyzer for 5 kilowatt scale of green hydrogen production. So these 5 kilowatt inverter system we use proprietary Victron inverter to make that. So if you see the
Mm-hmm.
figure one, it is there. The whole electrical setup we used proprietary solution, like we ordered three Victron inverter, connected them in parallel, and then made three-phase connection. So yeah, we published the paper in terms of like hydrogen and electrolyzer perspective, but never based on like the electrical or the PV system or inverter thing. It wasn't the focus of this paper. But in the first paper, sorry, the DC to DC converter one, we designed it in a small scale, but we couldn't scale it up. And about the first paper that I sent you was
Mm-hmm.
related to the inverter
Mm-hmm.
that we made. It was a DC to AC inverter that we made. Then we made a small DC to DC converter for hydrogen production.
Mm-hmm.
That also was successful,
Mm-hmm.
but we couldn't scale it up. Instead, we went to proprietary solution. So I ordered three Victron inverters, large batteries, 10 kilowatt hour batteries. Then we made the connections. We deployed the PV on pond. You can see there, and then we used a AC to DC converter to run the electrolyzer. The electrolyzer stack was 5 kilowatt, and it can generate up to like 1,000 liter of hydrogen in 1 hour. So it was a big project. So that's why we didn't take the risk to scale up the initial proposal of using DC to DC converter. Instead, we used the proprietary solution. And for the plasma generator, we made the DC to AC inverter.
For the membrane electrolyzer, did you get that off the shelf?
Uh, no, we have a company. So what was the project was about was like we were working with the company closely. They are like almost like they uh, it's a very new company, so they made the electrolyzer in their facility. We were doing the testing and integration, and they were very interested. Like, because like if you see the numbers,
Yeah.
if you use hydrogen, if you use grid power to generate hydrogen, it's never gonna make sense because the electrolyzer, which converts water to hydrogen using AC power, is like 60 to 70% efficient.
Mm-hmm.
If you just, or maybe you can, they claim the stack is 90-95% efficient, but the conversion process, it loses so many power. And then if you consider the fuel cell, which converts the hydrogen to electricity, that's very low efficiency. It's like 30-40%. So using grid power never makes sense. So that's why they collaborated with us. Like, and our proposal in both of those papers were like, you use uh, renewable power, only those fraction of power that you cannot consume, like the excess energy that we waste,
Yeah, exactly.
use that. Only that case it makes a economical sense. Otherwise, I won't suggest someone to produce hydrogen or drive your car using hydrogen. Maybe go electric. Battery is 95% efficient. Charger is like now it's, and the battery electric vehicle themselves, the motors are efficient. Why waste energy in converting it to hydrogen, then hydrogen to again um,
You
converting
said
that
the
to
the point of the approach was you're using basically excess power, basically load balancing. You're like balancing the loads and using that to make hydrogen. Yeah, yeah. Okay. For the one in the first paper where you did the 24 volt to 230 AC inverter, that was one phase,
single phase.
and um, you mentioned that that same driver. Wait, that driver
So
was.
I feel,
Wait, you said that the proprietary board had the driver, but you can get that same kind of driver as a single component, or other drivers as a component. You said you could run up to 10 of those MOSFETs.
so let me understand, like if I understand your question correctly or not. So you were saying like if I can get the MOSFET driver of same kind that can be controlled or like operated by a Arduino Nano and um, do the same thing, like do the inverting in, like make the inverter.
Yeah.
Yes, you can like you can find, like those components are not even up to the mark. As I said, like the board that has like EGS 002, the microcontroller in it is not as powerful as Arduino, and the MOSFET driver that they have is not as reliable as, like there is one company's MOSFET driver that I mostly use is Infineon. So if you look into the DC to DC converter paper, I use the MOSFET driver. It's like IR2104. So they are more reliable than the MOSFET driver they used in that inverter. But being an off-grid inverter, it didn't make any issue, and I just had to make a filter there to make pure sinusoidal. And if you see one of the results section, the PhD that we measured was like less than 5%, like 3 point something. So
Yeah.
it's even good enough to connect to the grid, even though it doesn't have the grid capacity, like grid connected capacity, but it was very good quality. And we got a, like we operated the plasma generator and it worked very well.
How much is one of those driver chips?
Yeah, yeah, I think you can find the better ones in market. So that was my next, like if you want to replicate this one, maybe instead of buying this off the shelf board,
Yeah.
maybe for one version you just buy this board. It maybe $10-12, order PC, order MOSFETs and make the breadboard. In a breadboard you can make the inverter, but in the next version I think you should design it using a Arduino and MOSFET driver, and you can make that inverter board by yourself. I don't think it's that difficult.
I mean, the main thing would be about the wiring plumbing thing. I mean, I think if we do something like a scalable, maintainable design, then the design goes into, okay, how do you connect all these things, plug them together, and interconnect them readily, so you can build one with one, you can build one with 10, you can build one with 20, and it's really no difference because it's plug and play almost. So socketable things, screw terminals, Wago connectors, however, or quick plugs, various things, especially that can be 3D printable and readily mass deployable. Um, is For example, if we use one of those driver boards, is there one that we can connect, or like basically snap it out to like the next bigger one, so we can run more of the power elements in parallel? Or I mean, what would be the easiest? How would you design this if you were faced with a problem? Okay, let's call it like an inverter construction set where you can plug in as many units as you like, and this is a more of an educational thing that still has real productive capacity. You can still use that. Okay, you can do like 5 kilowatts. You can do more. You know.
So, like, I cannot like final like comment on that. Like, what would be the exact issue that it might rise? Like when you connect infinite, like we are talking here, like infinite amount of MOSFET connecting in parallel. What would be the issue that the MOSFET driver will have, or what is the actual limitations? Of course, there are some, and how to overcome that. I think that's a maybe. Uh, of course, there are some, but I cannot like confirm you at this moment like what are the limitations. But I can look into it, and like maybe later I can like confirm you that, like do a little bit of study, and even maybe there is already a solution to that as well.
Right, right. I think the most useful would be something that's on a scale of say 1 kilowatt. You can plug in multiple units, so you can get to 10 readily, things like that. Um, and maybe there's one. Yeah, I have no idea. I haven't looked into the specific components, but looking at both price and feasibility and just the geometry factors that allow you to do it readily would be important. Where do we go from here? It sounds like, well, I mean, just the inverter that you did make, I mean, is a good model to go on. For example, I mean, there you've got pretty much a complete system.
There are several like videos on that in YouTube.
Uh-huh.
So it's not like it was one of my initial projects. So the purpose of that wasn't to just design an inverter. It was like making a portable trolley and then experiment and other stuff. But the original design of that inverter was like I designed the PCB and everything, but it was like based on already existing projects. So there are several projects, and one of them was like I think he went up to like 5 kilowatt using the same board because it's a proprietary board. Anyone can use it. So there are YouTube videos or GitHub repositories where people already implemented these, not for the plasma purpose, not for the PV inverter purpose, but for general inverter making purpose, like using battery to generate AC power. So there are like better maybe you can of course look into this paper as well, but there are several other videos that you might find on these board using the same board. Uh,
Mm-hmm.
it can be a very good starting point, and then later work on that. Instead of using the proprietary board, you develop the board by yourself, the control circuit, and use the heatsink and MOSFET combination. You can see like in the PCB as well, there is nothing, only the MOSFETs that are connected. Like
Mm-hmm.
in the actual PCB, if you so that what I started our conversation with, like this is what you were dreaming of. This is the actual uh, uh, actual experimentation was like this because the controller circuit was a separate PCB that slots into the rest of the power circuit. And in the power circuit, if you see, there is nothing. There are only 8 MOSFETs, and they are just connected.
Mm-hmm.
So you design the controller separately, and you uh, place your MOSFET as it is shown in the piece schematic, do the connection, and combine these two. So yeah, it's you can do that with the same board just designing the MOSFET on a heatsink, make the connections, and this same board can supply them. So you can literally use this, and in the next version, you might develop the board by yourself using Arduino. That can be a next version.
Mm-hmm.
So I think you can use this board and the design, and maybe using your MOSFET and heatsink idea, you can implement that easily, very quickly.
Mm-hmm.
And then in the next version, you design the board by yourself.
Mm-hmm. Okay. So if you had the battery input of 24 volts in that one that you're talking about, how did you get it to 240? Where's your transformer?
I showed you now in figure 16.
In figure 16.
Assembly, sorry, assemble the input.
Okay, and you've got all the components listed there, so that's good. Figure. Okay. Yeah, yeah. I'll take a look at this. I mean, that goes a long way already. Yeah. Um, where's your figure 16? Okay. I see. Great. And that transformer has to handle how much power? What was that rated for?
It was rated for, I think, 500. So this is not the transformer that we finally went with. It was for the, so we ordered a 500 watt. This one is, I think, 185 watt. So yeah, uh, but the same PCB can go up to like, just you change the transformer. This PCB can go up to like 2 kilowatt for sure. 2 kilowatt, yeah, 20 amp it can handle. The
Mm-hmm.
traces and all, it can handle 20 amp. So
Yeah.
that's the only limitations. But we didn't went with a bigger transformer because you can see like we didn't need it, like we didn't need that and for that experiment. And we did an experiment with 500 watt, uh, 500 VA transformer, and yes, you can literally connect a 2 kilowatt of inverter as well, sorry, kVA of inverter as well, but the size gets bulky. But it also does this one thing that you might want is like smoothing the sinusoidal wave from a staircase type squared AC signal, converts it to pure sinusoidal. This transformer, it has internal inductance and capacitor there, so it acts as a filter as well.
Mm-hmm. Mm-hmm.
But only limitations is for this application is having a transformer. But you can another solution would be you, instead of stepping it up at the output, you step up your battery voltage
Yeah.
first. So from 12 volt, sorry, 24 volt, you scale up to like 300 volt. So if you see that EGS002 schematic, their data sheet, they suggest you either you go with this, like invert, then step up. They have another solution. You step up your voltage, then supply to the same MOSFET driver. It will provide you a sinusoidal. In that case, the only limitations is like you won't get the full smooth uh, sinusoidal. It depends on the filtering, so the filter might be a little, it shouldn't be as bulky as a transformer, but you need to add a filter at the end. So you should look into that EG's S002 data sheet. So they have these two schematic, whether you use a transformer, step it up later, or you step it up first and then use this board to make it sinusoidal.
Right.
So that would be an option.
If we know, for example, we're running a 240 volt load, I mean, wouldn't it make more sense to connect to the PV at about 240 around that area? So batteries and PV at that high voltage.
That makes sense. That makes sense. But the problem with the battery is like you like the commercial batteries that you can safely handle, like handling high voltage of AC,
Yeah.
it's fine. But handling high voltage of DC, it's risky. It's life threatening. So 48 volt is fine. You can find easily. But exposed 240 volt DC, nobody would suggest you. Like a small spark or arc, it can go a long way. So,
You're
so
saying
that's the
from battery
safety.
what from explosion?
No, like the potential risk of like if you are making a DC bus with 600 volt or 300 volt, which is open, that's tricky.
Um,
So if you have a DC bus within your circuit, it's fine. But if it's like connecting multiple of the battery and getting up to 600 volt and then connecting the inverter to it, I think that would be a risky move. But if you have a PV, suppose 30 to 100 volt, and then scale it up to 240 volt or 300 volt DC in the inverter, and then invert it back to AC, I think that's more safe. But if you connect your battery in such a way that it reaches 240 or 300 volt, and then connect the inverter to it and make that configuration outside and leaving that bus bar open, I think that would be more tricky.
Now, that's in terms of how you actually install and
And
handle.
if you even look into the market, you won't find a DC circuit breaker, DC fuses of that rating, high DC voltage, because that becomes like the how the circuit breaker works is like the interrupting. So interrupting AC signal is very easy than a DC because DC is like continuous. So interrupting it at high voltage, creating that arc and suppressing that arc becomes much more difficult than AC because like AC has the tendency to go to that 0 point, and if you somehow uh, stop the circuit, sorry, break the circuit at that point, it is more easier. So that's why like when you go to like 300, 400 volt, getting a fuse and circuit breaker of that rating in DC, it's tricky. So
Mm-hmm.
that's why like that's why like they do that like in the inverter they have those brick forming inverters they have, but what they do is like within the inverter they have first one DC to DC converter which converts the PV voltage to a bus voltage that is maybe 400, maybe 300, maybe even 600 if you are considering a three phase, and then they convert it to AC. But all of those are inside the inverter.
Yeah. When a battery when a PV system is at like for example 500 volts or something, um, that's when they do this kind of strategy. When a PV is connected in a string, say of 10 of them at 30 volts, so you get like say 300 volts. That's what they do. They make it. They use the strategy that you just described.
They in that case they like you connect the PV in a in like series connections of like maybe 600 volt, and then directly plug it in into the inverter, and in the inverter they don't need actually to step it up, but everything happens so you don't make another bus to connect your battery. In those kind of situation you don't have a battery, so it's the PV and the PV. So in that case, those inverter are capable of handling multiple of those strings of PV panels. So you would see like there might be four terminals where the PV will be connected. So it's not just about the high voltage; it's the current. Then you will see like 600 volt. That's fine, but the current is like 10 amp, not more than that. So handling that is much easier, and you connect multiple of these 600 volt PV panel into the uh, inverter, and then from there they convert it back to AC. But
Yeah.
those kind of setup doesn't allow you to connect any battery to it.
Yeah. Just to clarify, if there's a person standing, there's a bus bar, and that bus bar is AC versus DC. I mean, the risk for touching it is the same, right? Or is it different if it's AC versus DC? I mean, I'm just saying, just for understanding the hypothetical scenarios here. There's no difference in the kind of damage that that kind of voltage does to you, right? But it's the question you're referring to is more like how switching occurs and how, like, outside of just the fact I'm going to touch these two leads that are at 600 volts. One is DC, one case is DC, one case is AC. They're both equivalently dangerous to that person touching them, right?
Uh, I would say like DC is more
Why is that?
because uh, because of like the continuity of uh,
The continuity
coverage.
of the load,
It won't give you that much of time
right?
that AC might give you.
You mean even that 60th of a second?
Yeah. Yes, I think so, and I
Yeah,
can refer to you. Like I can look into it, maybe do a quick chat GPT. I don't want to like nowadays.
yeah, yeah,
Everything that you ask, I just cross check with chat GPT first,
yeah,
then I say it because it's much easier. Like you have to confirm your thoughts. Like of course we have like so many thoughts, but it's now so easy. Instead, like either first you need to rely on someone who is knowledgeable in that field and then confirm your idea. But now I always
yeah,
refer to ChatGPT first, discuss with it to sound less like wrong in front of people. So yeah,
right.
I would prefer to do that instead of confirming this statement.
Yeah.
But yeah, I think so. I think so.
Okay. All right. That sounds good. Okay. So I think the
From the brightness, I forgot to turn on the light.
yeah. So I think the next step is to look into the so your existing inverter design and see how we want to work with that. I think that's a good start there. You would say.
Yes, like I think it supports the idea that you have, like modular.
Mm-hmm.
So if you see the model, you
Mm-hmm.
can see like the same heat sinks are there, the MOSFETs are there, the MOSFET pairs are connected in pairs. Like there were like two MOSFETs in the same leg, so two of them are side by side connected, sharing the same heat sink. So I think, and rest of the control circuit is there, and there is some voltage regulator that converts the 24 volt to 5 volt and 12 volt, which is required for the MOSFET driver, sorry, the inverter driver there. Apart from that, there is nothing. And there is a filter of a transformer and a capacitor that can be easily made. So the main power circuit is there only eight of those MOSFETs, and they're in exactly in same form factor that you were expecting.
Mm-hmm.
So instead of making a PCB out of that, you can play with that and maybe start with breadboard, then maybe made a 3D printed some kind of a holder which holds these MOSFETs and already when it is connected to their respective heat sinks. And the control circuit is there. You just make the rest final wiring and test your idea. And then the next step would be like, okay, let's make the inverter controller by ourselves. And I can assure you there are like Arduino Mega or Arduino Uno would be
Yeah.
sufficient enough for this, and there would be better MOSFET controller, MOSFET driver available in market in DGE. So I think you can, in the next stage, you can just make the uh, inverter driver by yourself, which is open source or programmable. I think that would be a very good starting point. And then there are several steps to reach that 100 kilowatt range or kVA range. I think
How would you
uh,
address the just because okay, it's going to be much easier to handle say 600 volts at say 10 amps from one string. So you got 6 kilowatts in that one string. Otherwise, if you leave it at like 48 volts, you just have to fatten up your cables. How would you address that? So going into say I wanted to put in like say 600 volts into your inverter and then have still a good system that does you say a grid power of 240 volts.
so. Unless you were like planning to use a battery backup, I think the higher the voltage that you can get, it's a good idea. Just don't just make the direct connection with your inverter and convert it to AC. That's what the grid connected or grid following inverter does. It directly connects the PV to it and then inverts it to AC. That's what it does. But if you are planning to interconnect battery to it, I think then the problem becomes like your battery voltage is like limited to 48 volt maybe.
Right.
They don't allow you to implement. Like I don't think I have seen any.
For one.
Yeah, but I haven't seen any. So I'm not sure like how much voltage that they allow you to connect in series those kind of batteries, because like, you have to reach that voltage level if you want to keep the PV voltage at higher voltage. So your battery voltage need to match that. But actually, most of the cases I have seen is like 48-volt battery that they connect, and in that case, your system becomes a little bit different. Uh, your voltage. So the inverters that I have seen, 3 kilowatt or 5 kilowatt, they accept 48 volt as a battery, and then they step up this voltage. Or what they do is like they connect PV. Maybe they would allow you to connect 200 volt of PV panel in series or 300 volt. What they're gonna do, they're gonna step it down to 48 volt, connect it to the battery, and then convert into AC and then step it up. Or they might step up the battery voltage and match with the PV and then convert it to AC. So they might follow this, but I have seen those kind of inverters which connects to the grid, then connects to the battery, and then connects to the PV panel. In that case, the battery voltage always I have seen is 48 volt. It's not the battery voltage matches the PV voltage. The battery
Yeah.
voltage is unique in sense of like 48 volt, 24 volt, and the PV voltage maybe they will allow you to connect 200 watt, 200 volt, 300 volt of uh, PV panel. But I would, if you are making off grid connected without battery, then I think connecting multiple of those strings in series and then get a higher voltage and directly convert it to AC, I think that would be much better. But if you are considering adding a battery, then I guess the battery voltage would be limited to 48 volt. Otherwise, there are already existing example that allows to connect you multiple of those batteries in to reach that higher DC voltage.
Hmm. If I go with battery-less and you got inverter going, the PV panels going straight to the inverter, um, say it was at 600 volts, is it easy to step it down to the 240 that I need for grid?
Yes, it's easier. I would say like the inverter even can do that. So it's not necessary that you would need a step, like you need to step it down and then invert. The inverter has the capacity to even for a certain extent it can regulate the output voltage as well. So it's not only converts from DC to AC, it can even regulate the output voltage, the amplitude of that. So having a higher voltage, maybe one stage of conversion is enough. But if you are considering a 48 volt battery, then there would be two stages of conversion. Either you need to increase the voltage to higher DC level, then convert it back to AC, or you convert to AC and then add a transformer at the end.
If we stay with batteryless and we can control the amplitude of the voltage going into the loads, are is actual so the current is increasing. We're not wasting power here. The current is increasing there. If you got
No,
600 volts,
we're not gonna waste energy here. Like these inverters are nowadays are like 98% efficient, and the higher the DC voltage, the higher the efficiency.
so say take the scenario of a 600 volt string, and we're converting to we got loads at you know say 120. Standard loads 120. What does that inverter do? So it's taking that 600 volts and then does what?
I'm not sure that the inverter that we will have. I I haven't seen an inverter more than 3 kilowatt with 120 volt. That's the problem. Like I have seen a split phase that you allows you 240 volt. That's more than 5 kilowatt, and only those takes around like 600 volt DC.
Okay, let's take that case. So what's happening there?
So in those kind of scenarios, I guess like if you have 240 volt, if you multiply it by three root over three, that like the minimum DC voltage that you require is 400 volt. So in
Yeah.
that case, yes, I guess 600 volt they don't have a additional stage of stepping it down to 400. I think they directly convert it to AC. That's my bet is because like I know the theory, but I haven't checked that like in the circuit by myself.
Ah.
But I think that they should be able to skip one level of conversion. But I haven't seen an inverter that is more than 3 kilowatt, but the output voltage is 120 because I think the national electrical code doesn't allow you maybe
Yeah.
for some reason
Right.
they don't do 20 amp AC. Then they go to directly split phase.
Yeah. Yep. Yep. No, that's fine. All right. Okay. Yeah. So I think we got a plan for now. I think look at your rework your existing design, go from there, and see if we can make the modular system based on that. Mm-hmm.
I think it would be a good start, and then maybe designing the controller by yourself. And the next stage would be to either incorporate battery or leave the battery and directly go into grid connected inverter system.
Mm-hmm. Yeah.
That would be the workflow would be in that way would be much better. And I think initially you will get a lot of um, resources available already that did this kind of experiment. But once you dive into that grid connected inverter thing, the lesser and lesser documentation you will find. Maybe you for getting experience on grid connected inverter, you might need to look into what are the if maybe I told you like there is a open source microinverter, so you might need to get some knowledge from there because they did that, they made that open source, so you might get more information from there rather than looking for a grid connection, a grid connected inverter. So yeah,
And
but
you said
at
that.
the beginning you will find a lot of resources,
Yep.
but when you go ahead, then you might find it difficult to get open source direct designs. So there, the complexity might come one by one.
Right. Right. And how far did you get on the microinverter that you are working on?
I was because like so currently I just completed that the power monitoring thing. So a plug which if you plug into the grid and then you connect it to the load, what's the waveform of the voltage, what's the waveform of the current, what's the RMS voltage current, and active power, deactive power, power factor, all this information to extract. I got that part right, and the next plan was mine was to use these inverter topology, like the already the inverter that I made, the inverter circuit. So I told you like the inverter circuit is same irrespective of what type of inverter you are making.
Mm-hmm.
So just my plan was to make the same inverter in such a way, just it synchronizes with the grid. So I already extracted. I was able to get the grid data, right? What's the exact phase of the voltage, what's the exact phase of the current, and active power, reactive power, all the information I already were able to extract. My next plan was to connect the inverter to the grid and synchronize it with that based on the data that I already have in my controller. So
Okay.
yeah, I divided the project into two parts.
Okay. How many lines of code does it take to follow the phase of the grid? How many lines of code does it take to do that? Is that a simple algorithm, or is that like a page, or is it one line?
I would say like it's not that difficult, but it depends on like so I one thing that I mentioned is like for single phase I don't think it would be that difficult. For three phase it is. So because like you have two parameters, right? The instantaneous, the voltage and current, all the time it's changing. So you cannot refer to a parameter that is changing. So suppose in DC quantity, you need 12 volt. In your feedback loop, you put 12. Maybe in 1 second you will reach there. Maybe in 2 seconds you will reach there, depending on your controller's performance. Or you, even maybe in 1 millisecond you will reach there. But think about now setting a reference for a AC signal that is changing faster than your uh, like you might think of. So it's you need to convert that AC parameter. Like there is a transformation that they call like Park and Clark transformation that converts the Park and Clark. So I can send you.
Direct quadrature zero transformation.
Yes, Clark and Park. Sorry. So yeah, what it does is like converts the sinusoidal signal to two DC quantities. And one of the quantities controls the active power, another one controls the reactive power. So the theory is very simple. It's not that difficult. You just feed one of the voltage or current, it will extract the DC quantity, two of those, and you then generate the sinusoidal signal from your inverter by controlling these two parameters. So it's like this one stage of learning that you might need. It's different from uh, all the other control algorithm. So it's just a conversion process that you need to implement in your code and then develop a controller around it. And the best kind of controller that we suggest in power system is PID controller. So it's old technique, but it still works and it works better with power system or power electronics. So PID control is like very traditional. So you know, like it's not gonna take a long to implement that code. Just to understand these and do this conversion and making it reliable is necessary. Like if you are able to do that, then controlling shouldn't be that difficult. Maybe the PID controller code should be like few lines of code. But I don't want to sound easy on this because I wasn't able to finish. So
Yeah.
like
Hey,
so
don't I have
it always sounds easier when you describe, but when you try to do, it's different.
a Park library? No, Park transformation library for Arduino. Maybe not.
Maybe, maybe not, but it's not. Even if you just look for the equations, it's very simple.
Yeah.
It's what it does is like first. So what I did was like able to extract the sinusoidal like each like output waveform of a sine wave of like voltage or current. I was able to extract that from the line. So I just needed to fit that into a equation
So you
that you can
did.
find.
What'd you do? You did a current loop, a pickup loop.
No, I haven't used that. So technically, yes, I used the Hall effect sensor, but it wasn't around the. It wasn't around the cable. It was in series. So I can show you that. So yeah, um, you're right. Like Hall effect sensor are more effective, but having a wire running through your Hall effect sensor doesn't sound that cool on your PCB. So what I did instead, like there is a Hall effect sensor, there are that comes in a IC form. So it has two legs, like the one that I use has six legs. So three of them where current goes in and three where currents go out. And then it has a ring around it which converts it to like the Hall effect process that converts it to voltage. And then it has eight more legs which connected to the control circuit. So it's basically doing the same thing. You put a wire, sorry, a Holophix sensor around the wire, but instead it has a IC that has like 6 legs to connect, flow the current, bypass the current, and it has 8 more legs to communicate with the controller, set the reference, get the data, these kind of things. So it's all in one chip. So there are several like these available, and there are several other IC as well
Hmm.
that are less reliable. But yeah, there are.
So you get the waveform, and then what do you do?
From there, so you get the voltage waveform and the current waveform, and then from there you can extract all the data. What are the phase? What's the frequency? What's the active power? What's the reactive power? And of course, the amplitude of the voltage. So now you have the amplitude of the voltage and the angle of the voltage. Now you convert that into two quantity, two DC quantity. That's called like Clark and Park transformation. And then this, based on these two parameters, you made the controller. The direct axis parameter will allow you to control any active power. So how much power you want to inject in your grid. And the second
Hi,
parameter
and
will
welcome
allow
back.
you to control how much reactive power you want to control, adjust. Of course, you want to keep it to zero. So thus, it allows you not only to synchronize, but also how much active power you want to feed to the grid. And these Park and Clark transformation, what it does, it takes the phase of your voltage and the amplitude of your voltage, these two parameters, and feeding into that equation, you can just, it will give you two DC components that I'm saying. And there is another loop that's called PLL, phase lock loop, that extracts the phase data. Because like you can get the voltage, current, instantaneous values, the points, but the phase angle you can get from that PLL, phase lock loop. So these are the simple things that are like well established. Everyone uses that. There are like several simulation model equations. What would be the PID controller's value to control these kind of things? They are available everywhere. There are thousands, hundreds of course, thousands of paper available. And I think one of the in the microinverter they use the same thing. So I can give you the code even. The yes, they use STM32. I haven't checked that because I didn't went that far to like look into the code how many lines, but I think it shouldn't be that like
Yeah,
that much difficult as it sounds. But making it reliable that might be tricky.
yeah, of course.
But, but I don't think the process would be that difficult.
Hmm. Hmm.
Like the theory is not that difficult because like it's well established. It's not like every day there is a new theory that's changing or changing everything. So it's there for like many years and it's reliable. PID controller reliable, Clark and Park transformation reliable. Same thing. Everyone is using that.
Hmm.
So that is the good thing about power system. Nothing changes rapidly like software or programming. They change every day, but this one is not. So
I
yeah.
mean, conceptually speaking, easiest thing would be okay. So there's a say there's a, is there any turnkey thing that you just put around the your grid wires? You plug it into your grid, and it gives you that signal that you can say then feed to an Arduino to give it the timing. Is there anything of that nature where you just have a module that gets you that timing information into a another microcontroller? Have you ever heard of anything like that, or this is like too custom? This just doesn't exist.
It exists. Like so, the same thing. Like you order a Hall effect sensor, clamp sensor that they call. It will give you the current value and the phases. So it converts into DC. You just feed it to the Arduino Nano, and you need the voltage. So you just connect. So what you can do. So first there is a cheap method that is like suppose you have a 120-volt AC output. You just connect two wires to that, and then use a voltage divider in between. So you step it down to like 1.6 volt plus, 1.6 volt minus. Then you put it into a open circuit, level shift it, because like microcontroller won't be able to read minus values. So you level shift it between 0 to 3.3, and then feed it to the microcontroller. Microcontroller would be able to read it, and then shift it back to 0 where it was initially. You get the AC output voltage and AC current value from the grid. This is the easiest method. But it's not safe because you are connecting AC to a voltage divider. That means literally you are shorting it. So anything going wrong can damage your circuit. So you can use a small transformer, very small teeny tiny transformer that doesn't need to be a maybe zero point 0.5 or 0.25 watt of inverter should transformer should be enough, or 1 VA or 5 VA enough, like a small transformer that step down your 12 volt to suppose 3.3 volt or 5 volt, and then you step it down further to be able to read by the microcontroller that you have.
You
So
went
this
from
is
120
two
volts. You put
process.
this on the AC line.
So you can directly connect. You can directly connect. Make a voltage divider out of it, and then measure the voltage directly. It's not safe practice because in AC, if you are making a voltage divider between 120 volt, it's not safe. So it works. The cheap power monitoring device that we have, I can show you one. Those are like 30, 20, 30, $35. They use the same principle. So this is one of the first one that came. So it's like what they use is like if you open it, they will have a resistor that is like a high power resistor, but very low value. So once the current flows through it, so being a very low resistor, the voltage across it will be fluctuating based on how much current is flowing. You just measure that voltage, you literally get the current. Because if you measure the voltage divided by the resistance, you get the current. So instead of using a Hall effect sensor, they use a resistor. And they have a voltage divider circuit somewhere else in the circuit, which steps down this 120 volt to readable voltage by the uh, microcontroller. Then they use a MOS op amp to level shift it, and then they use a microcontroller to read it and then level shift back. So this is the cheapest option that you have. And then if you go to the next stage, maybe you can add a clamp meter to around the wire, connect it to the Arduino Nano, Arduino Uno, Arduino Mega. It will be able to read that current, and use a transformer to step down the voltage and then send it to the op amp, filter it out, and then connect to the any of the analog pin of your uh, Arduino Mega. It should be able to read the voltage. So that's the best practice, and this is the cheapest practice. So it depends like which inverter using which technology. That's why like the failure rates comes like which inverter that you are going with. Like you can make an inverter with very cheap alternatives or options. But failure rate would be higher in that case if you are just using a MOS resistor. So the problem with using a resistor as a current measuring thing. So how it measures is like current flows through the resistor voltage across the resistor, the voltage increases or drops based on the current waveform, right? But if the resistor gets hot, the resistivity drops. So now at the beginning, the resistor value were known. That's why you were able to divide it by the voltage that you measured, and you were able to obtain the current.
Yeah.
But when the current is higher or the inverter is on for a while, now you start to see the difference between the actual voltage
Yeah.
and the measured voltage, because once it is operational, you cannot calibrate your system anymore. So these are the limitations that they come
Yeah.
with.
Okay. So for the AC inverter that you did from DC, would that same system with the components you have chosen work for an input that's? 'Cause I think you had it for what, like whatever, a single panel or a couple of panels or whatever. Would it work for an input of say 600, or that the components in there don't handle that? You would just have to change out the components, right? We use the same design, take the components that can handle it, right?
Mm, that was meant for like off-grid
Yeah.
application.
Yeah.
So first of all, that's not meant for grid connected application. So
Right.
that's the first thing that you. And if you want to work with, but if you look into the datasheet,
Mm-hmm.
so there is a control part, there is a power electronics part. The power electronics is easy to answer. The thermostat is the VGS, like a gate to source voltage. Sorry, DL, drain to source voltage. If that is higher than the voltage that you are putting across it, if it's lower than that, you have to like change the component to match that level. So the drain to source voltage should be higher than the voltage that you are planning to put in the input.
Yeah.
So you just select the right component for your right amount of voltage and current, it should be working fine. But the problem is in the controller. The controller has, I already mentioned you, like it allows you to connect high voltage of DC. Instead of the topology that I used was like use low voltage battery, convert it to AC, then step it up using transformer. But they have a same method that the same inverter module, like controller, can work or function properly if you apply 300 volt or 400 volt AC, sorry, DC. So that will work. So just look into, I would refer to their datasheet, that they have another schematic reference that you can follow. And if you make your circuit in such a way that you are able to supply 400 volt DC to the this inverter, the inverter module or the inverter driver would be able to convert it to AC. It either it is 230 volt or 120 volt, it would be able to do that. So
Yeah.
the same components, but I'm not sure 100% about the components that I have selected. Maybe they are not enough. If I'm not wrong, I have used like 100 volt and 100 amp rated MOSFETs. Maybe you need to choose 600 volt rated MOSFETs. That's it. The
Yeah.
current rating should be the same, or even lower. The current rating should be enough, because like now you are handling more voltage, less current.
Mm-hmm.
So 600 volt, 50 amp, or 20 amp, 30 amp MOSFET should be enough.
And
So
higher
yes, the
voltage
schematic is there already.
and higher voltage MOSFETs are more efficient, right, than lower. You don't have
Yes,
to make.
the ohmic drop will be less in them.
Yeah.
The conduction loss will be less. Yes.
Sounds good. All right.
There are like different aspects, but I think it's a good point to start, and then there is a long way to go. But I think like the idea that you have, I think that's uh, applicable, or you can like.
Yeah. I mean, the inverter part is the same. The thing that we're gonna have to worry about is another module for reading the phases and all that, to do the phase lock and all that.
Yeah.
But that's on the brain side. The power side stays the
Yeah,
same.
the power side is same. That was my plan, was like to start first monitor the power.
Yeah.
So then control it, try to like how to develop the controller,
Yeah,
and
yeah.
use the same power electronics circuit to synchronize with the grid. So the power electronic circuit is always the same, almost more or less.
And for synchronizing with the grid, though, you wait. Let's see. You want STM32 level performance minimum? You said, or is that not even enough?
No. I think the micro inverter that I was initially following, he did it with STM32. But I think and the power monitoring device that I was able to make was based on STM32. So there was nothing, no ADC required, external ADC. I just converted. So I mentioned you like I used a Hall effect sensor that measured the AC current.
Mm-hmm.
Then I just used the op amp to level it up, and then directly I fed it to the STM32. There was nothing extra that no extra circuit. So the STM was capable of measuring it very well compared to the Arduino or ESP. So it has, and it's reliable. So suppose you every time you turn on the inverter or your electronics device, the chances of functioning properly is way higher in STM32 than any Arduino chip or ESP for sure. Arduino would be, I will place it in second place. STM, like, I won't say that it's on my experience. What I have learned from those online resources is like it's more reliable for power electronics application. But if you are doing prototyping, Arduino is your go-to option. If you are doing something with server, Wi-Fi, these kind of things, ESP would be the better option. But if you are doing something with power electronics, I think STM would be a better option to
And,
start with.
and for the open source microinverter project, was the power stage similar to yours, or pretty much the same? Of course, different. I guess different components for smaller power. But I mean, beyond that, that's like there's no rocket science in the power stage, right?
Yeah, no, it was almost the same.
Yeah.
It was almost the same.
Okay. Sounds good. So yeah, there's a lot of good resource. When I looked at the a few years ago, the microinverter project was not even out there yet. That must have been a few good years ago that I looked last. But yeah, it's good to see that. There's the microinverter project. There was another open source inverter project. I forget what it was that popped up this time around since I looked last, which was a long time ago.
Yeah, no, like, and also I think Europe allow you to connect microinverter directly to your outlet now.
Oh yeah.
So suppose so that's a very good. Like I won't be able to say that it's a good thing or bad thing because they also went through the recent blackout thing,
Yeah.
and somehow solar or renewable is responsible for that, like that cascading effect. Because at that time I think 70% was uh, renewable. So yeah,
How do they, if you
that's
do
like,
that, one question that pops up, if you have micro inverters plugged right into the grid, how do you do islanding protection in that case? They also turn off when the grid goes down?
so if it were like these, it was fine. They have most of the inverter has like anti-islanding protection, so it still keeps connected until the volt. So if you are talking about like 60 hertz, so the range is very wide, 55 to 65. So if the frequency is 58, it will change the frequency to 58. If it's 57, it will change to the 57. That means it tries to follow the read as long as it can within a band. So if your read is strong, it's following a strong reference, it's fine. If your read is failing, your ship is sinking, it's gonna sink with that too. So it will make the situation worse. Like suppose your ship is like shaking, and someone is there who is also shaking with you and participating it with that, so it will make the sink more rapid. So that's the problem that I assume that happened. or everyone assumes that's happened, like because 70% of grid at that time was dependent on inverters. But now the solution that they are referring, or I when I was in doing masters, it was grid forming inverters. So instead of relying on grid, they can form a grid. So it's not always following the grid. They can generate with AC supply without having a grid. So they make the grid stronger. So initially the idea was we have a strong grid, let's follow it. But now if your system has 70% renewable, it's not strong anymore. Everyone is relying on each other. So if there is anything wrong, there is nothing to, like there is nothing, like we call it inertia. So there is so less inertia to prevent this kind of blackout. So that's why now people are trying to push the grid forming inverter topology, like that is not only relying on grid, that can form the grid. So this is like latest technology. Now there are few inverters. I think in Australia they are already implementing it widely, and I think the other countries will do the same thing.
So does the grid at
And
that
there is a
point?
micro inverter that can do the same thing, grid forming.
So at that point, the grid has to follow the off grid if it turns back on.
No, actually, it's like generator. The power plants that you have, instead of following like a conventional generator, it will be swinging. Maybe it's going to be swinging. That means it's going to supply active power. It's going to supply reactive power whenever it is necessary. It's not going to be like following all the time, controlling the voltage only. No, it's gonna swinging between like the synchronous condenser or synchronous generator. What they do is like they are able to supply you the active power that is required. They were able to supply reactive power that is required. The grid following inverters are not that extent, but the grid forming inverters can do the same. Like even in some instances there is not enough requirement of active power. Even in that scenario, the grid forming inverter will participate, still connected into the grid, and supply reactive power. So it's like mimicking the conventional power plant.
Well, what happens when the power plant goes out and then it turns back on, or the line is connected back? How does it interact with the formed grid with the inverters? You're saying it syncs
So
with automatically?
it's called black start. So it's like suppose all the generator in the world. I'm referring the power plant as generator. All the generators in your grid, suppose in US, are shut down. So what's the process to start it? So that's we call like black start. So you have like one or two big power plants, the larger power plants. You need to start. So that forms the grid, and then rest of the power plants starts one by one, which follows it. So it's not like the diesel power plants or gas turbines or the nuclear. They always form the grid. They also follow each other. So it's the same. There is another entity now in the grid, which is grid forming inverter, that can do the same thing,
So they
and
have
that
to
can even
switch
do
from
the black
one.
start as well. It can now, it's so reliable that it can do the black start as well. You can, if you have a big solar plant,
Okay, I get it.
it can start it, and even your diesel power plant can follow it. Because like if you have a big power plant, suppose nuclear, then your diesel power plant need to follow that, and it's made in such a way that it follows it.
Yeah, I mean that's micro. Yeah, I mean we have to master this technology here as microgrids because we'll have power coming in from all kinds of sources, from wind to biogas and everything. So we'll have
So
to.
like there is a very good scope, or still there is a very big opportunity in terms of like renewable here at least. Like there is a problem that is being caused by the renewable, and renewable is the one that is solving that as well. So that's the good part.
Yeah, oh, that's good. That's good. Excellent, excellent. Okay. Um, yeah, yeah.
So yeah, I think if you like, you can start with these, and like I'm always here. First lab is always here, and Professor Pierce is here. And in our lab is like there's several people still working on these projects, and I also go there very often, like almost every week, because like here I am like working like during my weekdays, and then I go back to London and then spend my weekends there, and then come back again and work here. So yeah, so like in any kind of information that you might need, or if you plan to like collaborate, because like our lab has like almost all the resources that can build the system around your idea. So maybe we can uh,
Yeah, yeah,
we can share that in future as well. With professor is there, and other team members are there, and I'm of course there. So yeah, I
so
think
Professor Pierce, he's getting nominated as a Thompson Fellow. Do you know about that program?
yes, like a little bit. I think he's the director of that. So yeah.
Yeah, so we're going to collaborate more closely. So I look forward to all of this. This is, I think we're going to step up the collaboration between open source ecology and FAST. That would be good. I like the FAST metaphor. That's exactly right. I saw Dr. Pierce's presentation on that. Good presentation. That is exactly the kind of more. We need more of that kind of discussion of how open collaboration just beats all barriers in terms of development speed. Yeah, really good. So I look forward to that. Okay. Well, thank you for your time. So yeah, we'll be in touch and we'll move on the design.
Yeah, sure, sure. I'll be in the loop. Like whenever you want to like share any progress, or if you want us to do any part of your experiments in our lab, or like
Yeah.
with me as well. So we are like always available, and of course I am as well. So you can reach me anytime,
Excellent.
and we can have like in this kind of chat anytime you want. And
Yeah.
of course, we will be working with Professor Pierce, so I am still in touch with him, and like with the rest of the team members. So of course, like if you, I'll be in touch for sure.
Okay. Excellent. Well, thank you for your help, and I look forward to more in the future. We'll see where we take this. Open source power electronics for the world.
Yes, that sounds good.
Okay.
Okay, then have a good night then.
Have a good night. Thank you.